thinking about this as a bit of an alcove on alcove, except that we're trying to provide maximal contrast with in terms of organizational competence. So as you notice, we didn't plan any games or any breaks or like any civilized people would have, but there is a 5-minute break in between the sessions at the end of the hour. So without further ado, I'd like to welcome Sam Hopkins, who will be giving us a talk on involutions on Dyck paths and piecewise linear and birational lifts. Take it away.
Yes, thank you, Tom. Thanks to Tom and Dari for the invitation to speak here. Yeah, first let me make a disclaimer. So I think the letters in this seminar series acronym stand for algebraic and combinatorial perspectives in the mathematical sciences, or something like that. I'm going to be very heavy on the combinatorial side of things to start off. But if, like me, you're in the States, probably you're just waking up right now, so that will mean it's easygoing to start. I think we'll get a little more algebraic as the day goes on. And let me also say that this is all joint work with Mike Joseph, who is here to I guess, lead the discussion after. Okay, so I said I'm going to be heavy on the combinatorics, and to start off with, I'm going to review some very famous combinatorial sequences of numbers, Catalan numbers, Narayana numbers, as well as Dyck paths, which are the main combinatorial object I'm going to be interested in, and the Lalanne Kreweras involution, which is a certain operation on the Dyck paths. And since I guess the seminar series is mostly based in Europe, I thought it would be nice to include a nice picture of Europe there. So you can try to understand or interpret the meaning of this as the talk goes on. Yeah, so let's start off with the Catalan numbers, a very famous sequence of numbers, 1, 2, 5, 14. Hopefully most of us have seen these before. I noticed at the Alcove seminar, which Tom mentioned, they kind of started up with another 1, 1, 1, 2, 5. So maybe I should have done that because it's very reasonable to let the 0th Catalan number be 1 as well. But anyways, these numbers have many interpretations. So for example, triangulations, different kinds of trees, binary trees, plane trees, ways of carrying out multiplication of terms in an order, so bracketing, as well as hundreds of others, which are recorded, for example, in an exercise in Richard Stanley's Enumerative Combinatorics Volume 2, as well as he has a new book about all the different interpretations of Catalan numbers. And they have a well-known product formula, which can be written in a couple of different ways, but here I'm choosing one of the standard ones. So 1 over n plus 1 times 2n, choose n, central binomial coefficient. So these are a very beloved sequence of numbers for combinatorialists. And there's one particular interpretation that I want to focus on, which is in terms of Dyck paths. So a Dyck path of length 2n is a lattice path in the 2-dimensional grid from the point 0, 0, the origin, to 2n, 0, which has n up steps of the form 1, 1, and n down steps of the form 1 minus 1, and it meets this condition that it never goes below the x-axis. So it looks like a mountain range like this. So here's one example for n equals 10. We start off with some up steps, down steps, okay. And it is well known that the number of Dyck paths of length 2n is the Catalan number Cn. So for example, for n equals 3, the number of Dyck paths of length 6 is 5, the third Catalan number. By the way, please stop me at any moment if you have questions, and I can see the chat, so if you type them there, that's fine too. Okay, so yeah, Dyck paths kind of look like mountains or mountain ranges, so often use topographic terminology. So for example, a peak in a Dyck path is just kind of what you would think it is. So it's an up step that's immediately followed by a down step. The red dots here are peaks. Can you all see my mouse when I move to, yeah, okay. And then a valley is sort of the opposite thing. It's a down step followed by an up step. So it's these green dots here are valleys. And a simple observation is that any Dyck path that has k valleys has k plus 1 peaks. So counting according to peaks or valleys is basically the same. I'm going to focus on valleys, which is just kind of easier, but it's just a simple change of index. Okay, and so with those definitions, the Narayana number, nk, is the number of Dyck paths of length 2n with exactly k valleys. So here's a kind of triangular array of the values of n and k for small numbers, n and k. So for example, this is saying that there are 6 Dyck paths of length 8 with exactly 1 valley. Okay, and so it's clear from this definition that the Narayana numbers refine the Catalan number in the sense that if I add up all the numbers in one row here, I get the Catalan number. So 1 plus 6 plus 6 plus 1 is 14, which is the 4th Catalan number. And they're named after Narayana, who in 1959, well, he gave a formula for them. So it's kind of similar to the Catalan number formula, 1 over n times product of binomials, n choose k, n choose k plus 1. Okay, and so that's a nice formula. And one interesting fact about this formula, if you stare at it for a second and do a little bit of, well, you know, the fact that like n choose k is the same as n choose n minus k, then you can see quite quickly that there's a kind of symmetry that the Narayana numbers exhibit. So nk is the same as n minus 1 minus k for all k. So in other words, easier way to say it is if I look at this, a row of this table, it's symmetric, right? I see 1, 6, and then 6, 1. Okay, that's interesting because, and here's an even simpler case, the third row, 1, 3, 1, that's a symmetric sequence or palindromic sequence. But it's not combinatorially obvious why the number of Dyck paths with k values should be the same as the number with n minus 1 minus k values. And Narayana's proof of this formula doesn't really illuminate that fact. It was kind of just inclusion exclusion type argument or evaluating a determinant. So there's some kind of counting with signs and it just works out this way. So you might want to have a more combinatorial way of seeing this fact that there's this symmetry in the number of values statistic. There's kind of an obvious symmetry that Dyck paths have, which is just reflection right across the vertical axis, but that doesn't change the number of values, of course, so that's not going to explain this symmetry. There's something more interesting going on. Okay, and so the Lalanne-Kreweras involution is a map on Dyck paths which combinatorially demonstrates the symmetry of Narayana numbers in the sense that the number of values of a Dyck path gamma plus the number of values of its image under the Lalanne-Kreweras involution is constantly equal to n minus 1. So we pair up complementary values. And here's what the Lalanne-Kreweras involution looks like. So we take our initial Dyck path gamma drawn in blue here. It has 4 valleys. And then we do something kind of geometric. We look at every position that's either a double up step or a double down step. And we draw lines, those dashed lines emanating from the midpoints of those double up steps or double down steps. And the dashed lines are going to meet each other at corners. And those corners will uniquely determine another Dyck path, but drawn upside down, whose valleys occur exactly at the places where those dashed lines meet. So hopefully this picture is showing what's going on. In a moment, I'll give you another definition, which is a little bit easier to work with, but this is a nice pictorial representation of what's going on. And so there's some things you can check. So like we have 4 plus 5 equals 9, which is n minus 1. Another thing is that this map really is an involution in the valleys determine the path. That is true, Jim. If you know the positions of the valleys, then you know the Dyck path. And that's kind of true more generally. Yeah, I mean, obviously not every possible collection of positions could be the valleys of a Dyck path, but there can be at most one Dyck path. And I'll explain more about that in a second, I guess, as well. Okay, and so this is an involution. So if I do it twice, I get back to the original Dyck path. So you can kind of see that if I were to draw dashed lines emanating from the red midpoints, that they would intersect exactly at the valleys of the blue Dyck path as well. Okay, so let's keep going, but have this picture in mind. So this is like the main object construction I want to study and generalize, this involution on Dyck paths. But I'm going to switch to a more poset theoretic description of it right now. So let's reinterpret this involution in terms of a certain partially ordered set that I'll denote delta n-1. So what is delta n-1? It's the poset whose elements are intervals. So I use this kind of bracket notation for them, I, j. So the numbers between I and j for I and j between 1 and n-1. And the partial order is given by inclusion of intervals. So let me just show you what these look like, because it's a little bit easier to understand with an example. So first of all, the reason I use this notation delta is because it has a kind of triangular Hasse diagram. And I'll just show you the first four all at once. So again, the order is inclusion of intervals. So for delta 4, we're looking at intervals ij with I and j between 1 and 4. The smallest such intervals are singletons, right? So they're of the form 1, 1, 2, 2, 3, 3, etc. But 3, 3 as an interval, like the numbers between 3 and 3, which is just 3, is contained in the numbers between 2 and 3. So that's why there's this order relation here among those two elements. So yeah, it's quite easy to think about in terms of intervals, but just don't get mixed up, because it's not the usual kind of coordinate order. Like you have this funny thing where ij is less than I prime j prime if I prime is less than I and j is less than j prime, right? But okay, is the definition of this poset clear? It's also the type A root poset. Maybe I'll mention that later, but for now, I'm just defining it in terms of intervals. Okay, and so now what we're going to show is that the antichains of this poset are the same as Dyck paths. So recall that an antichain of a poset is just a subset of pairwise incomparable elements. So none of the two elements in my antichain can be related by an order relation. And we use A of P to denote the set of antichains. So now let me show you how the Dyck paths of length 2n are in bijection with the antichains of this poset delta n-1. Again, it's kind of a pictorial bijection. So we draw the Dyck path starting sort of one level below where our poset starts. And all we do is wherever we see a valley, immediately above that, we fill in the element of the poset. We include that in our antichain. So here's a Dyck path of length 10, and it corresponds to this 2-element antichain in the poset delta 4. Yeah, so again, it's just this kind of visual thing where you mark the positions of the valleys. So notice the number of valleys is, of course, then the cardinality of the antichain. And via this bijection, we can view the Lalanne-Kreweras involution as an involution on antichains, which has the property that the number of elements in the antichain plus the number in the Lalanne-Kreweras involution is this constant n-1. And once we move to this poset perspective, there's a more, well, kind of algebraic definition of the Lalanne-Kreweras involution, and this is due to Penichev. So how can we compute the Lalanne-Kreweras involution in terms of these intervals? Okay, so let's write our antichain A as a collection of intervals I1, J1, I2, J2, etc. And let's order them so their first, coordinates are increasing. I1 is less than I2, etc. Then to compute the Lalanne-Kreweras involution, which I'll do I prime 1, J prime 1, etc. What I do is, well, the first coordinates of the Lalanne-Kreweras involution are the complements of the second coordinates of the original antichain, and vice versa. The second coordinates of this LK of A are the complements of the first coordinates of A. Okay, so a couple things are very clear from this, assuming that this definition is correct. So first of all, it's an involution, because if I do this swapping and complementing thing twice, I clearly get back to where I was. And also the fact that, you know, we have the sum of cardinalities equals n-1 is clear, because the number has to add up to n-1. But now let me show you an example to make it a little more convincing. So I start with this Dyck path here. I think it's the same one I had before. And it corresponds to some 4 elements anti-chain in delta 9, which is, you know, these coordinates 1, 2, 4, 4, 5, 6, 6, 9. Its image under the Lalanne Kreweras involution is this other red Dyck path, which has 5 values, 5 element anti-chain, 1, 2, 3, 3, 5, 7, 7, 8, 8, 9. And the point is that these first coordinates of the LK of A, 1, 3, 5, 7, 8, are exactly the complements of the second coordinates there, 2, 4, 6, 9 from the blue antichain. And similarly, 2, 3, 7, 8, 9 are the complements of 1, 4, 5, 6. So this is a nice alternate definition of the Lalanne Kreweras involution in terms of the posets and these intervals. So it makes a lot of the properties immediate. Okay, any questions about that? So this is really the operation that I'm trying to generalize and understand better. This is kind of, I'm sort of like, this attribution is a little wrong because Peniushev didn't know about the Lalanne Kreweras involution. He just defined this operation on antichains and observed that it has these properties. So, anyways, it's not too hard to see that it's the same map as the one that I mentioned.
Sorry.
Yes, question, sorry. No, okay. So I'll keep going then. Okay, so now I'm going to get to stuff that's a little bit, hopefully, maybe connecting with some of the things from later in the day. So toggling is kind of an operation on antichains of a poset that has been applied a lot lately to understand these kind of dynamics. So our first new result is a way of expressing this involution in terms of something called toggles, which are local involutions. Okay, so I have a poset P and an antichain of my poset, and I'm going to fix some element little p. So toggling little p in A is an operation on antichains that produces a new antichain tau sub p of A, where what do I do? Well, if P belongs to my antichain, then I take it away. If P doesn't belong to my antichain and I can add it and still be an antichain, then I add it. And otherwise I do nothing. So toggling changes the status of P in my antichain where possible. Let me show you an example. So if the P is this 3-element poset XYZ, maybe I'm starting with this antichain that just has X in it, and I toggle at X. Well, I can always remove it. So if X is there, then I take it away and I got the empty antichain. If I start with the antichain that's just Y, then I can add X, and so I do. If I start with the antichain that's just Z, I sort of try to add X, but adding X is not allowed because that would not be an antichain if Z was there as well, so I just do nothing. And so, yeah, so these are toggles. They are involutions. If I do them twice, I stay where I am. Okay, and so, yeah, so let me keep going. But what we're going to try to do is build up the Lalanne Kreweras involution in terms of these toggles. But first, I need a couple more technical definitions. So a poset is ranked if basically we can write it as a union of ranks so that the edges of the Hasse diagram go between the ranks. So it sort of has this slice by slice picture. And it's easy to see that two toggles, tau p and tau q, commute if p and q are incomparable elements. So that means that for any fixed rank, we can kind of consider the operation of toggling everything at that rank at once, because all of those things have to be incomparable. So I'll use tau sub I for I equals 1, 2, up to R, the number of ranks, to denote the composition, all the toggles at rank I. So here's an example. We want to write an involution as a product of involutions. Yes, that's a good point, Tom. It's kind of funny, but anyways, you'll see why in a second that's useful. But that's true. So I'll mention this in a second, but the fact that the taus are involutions doesn't mean that, you know, any combination of them is an involution, right? Of course, like in the symmetric group, you know, it's generated by involutions, but well, not every permutation is involution. Okay, but let's look at tau sub 2 on this poset. So I just toggle everything at the second rank. That thing on the left, I cannot add it because there's something below it. The middle one I can add, so I do, and the right one I remove. So this is what I get. Okay, so that's just showing you one example of these rank toggles. Okay, let me mention row motion because a lot of people here have thought about this. So row motion is the composition of all the rank toggles from the bottom to the top. So tau 1, then tau 2, etc. up to tau R. So here's an example. I'll do this quickly, but start with this anti-chain. We toggle everything at the first rank. That's going to remove the rightmost thing and do nothing to the other ones. Then at the second rank, we apply a toggle that's going to remove the left and then add the right. And then at the third rank, we try to toggle, but there's nothing we can do. We can't add. So this is the result of applying row motion to my original anti-chain. So as I mentioned, it's been studied by many people, especially lately. Here are some names associated with row motion. And it's kind of a key player in this emerging subfield of dynamical algebraic combinatorics. So row motion is invertible. In fact, any composition of the toggles is invertible, but it's not an involution. Let me show you. So if I start with that, the row motion of A, which I'll denote A prime here, and I apply row motion again, okay, I get something different than A. It's just a different anti-chain. And in fact, for this particular poset, the delta n-1 poset, row motion has order 2n. So that means that if I started with that original A, I have to apply row motion 8 times to get back to where I started. You might think that's a lot, but actually row motion is very well behaved for this poset. That's a small order 2n. For a random poset, row motion behaves very chaotically. Its order will be much larger generically. So anyways, this is an example where row motion is well understood and behaves very nicely, this particular triangular poset. But of course, it's defined for like any poset. Okay, but that was sort of just an aside or connecting to previous work. What we showed is that the Lalanne Kreweras involution can be written as a composition of toggles. So here's the composition of toggles you need to do. These are the rank toggles, remember. So I'm writing it in the kind of functional notation. So we start at the right? So the first thing we do is tau 1, tau 2, etc. up to tau n-1. So that's, that actually is just row motion, everything from bottom to top. But then we do the same thing where we skip the first rank. So we do tau 2, tau 3 up to tau n-1. And we keep going. So we do tau n-1, tau n-2, n-1, and then we end with tau n-1. So we just kind of drop the initial part every time. It's a lot more toggles, right? It's like quadratically many or something. Okay, and so let me give you an example, a small example. So here's the Lalanne Kreweras involution as a map on Dyck paths as well as on antichains for a small case of n equals 4. Let's compute this using toggles. So we toggle at rank 1. We remove the rightmost thing. We toggle at the second rank. We add the rightmost thing, remove the leftmost. We toggle at rank 3, that does nothing. We toggle at rank 2, now we add the left and remove the right. We toggle at rank 3, that does nothing. We toggle at rank 3, that does nothing. So you can see a lot of these do nothing, but anyways, what we end up with is indeed the anti-chain on the right, and we show that that's true in general. So that always carrying out this composition of toggles gives you this Lalanne Kreweras involution. Okay, is that clear? So these definitions make sense for any ranked poset. So we can more generally define Rowvacuation. This is kind of a funny name, but anyways, you can consider this composition of toggles where you go from the bottom to the top, and then you skip the first and go from the second bottom to the top, and so on. by the same formula. And it's true in general that, well, Rowvacuation is always an involution for any poset P, and it conjugates row motion to its inverse. So basically, row motion and Rowvacuation together generate a dihedral group action on the set of antichains. This is like, this is not hard to prove. It's like a very formal proof, and it actually follows exactly the proof that Schutzenberger's promotion and evacuation operators acting on the linear extensions of a poset satisfy analogous properties. So it's kind of, yeah. So there's nothing too deep going on here. The fact that you get an involution for this is just some kind of formal mumbo jumbo. The fact that, yeah, it's basically an identity that holds in the right-angled Coxeter group set, generated by these taus. Okay, but that's just an aside to say that what we've shown is that this Lalanne Kreweras involution is a special case of a more general construction that is defined for any ranked poset. Okay, but let me keep going and finally try to get to the topic of this seminar, which is about birational stuff. So the real reason we wanted to write the LK involution as a composition of toggles was not just for the sake of it, but it was in order to extend it to the piecewise linear and birational realms. So this is a recent trend that's been very popular in combinatorics, algebraic combinatorics. It's the idea that we can take some known constructions like rowmotion or the RSK algorithm or evacuation, jeu de Tequin, and we can realize those operations as piecewise linear maps. So things involving plus and minus and min and max. And then we take those descriptions of our combinatorial constructions and we quote unquote detropicalize them, which is some procedure that takes the piecewise linear expression and it makes a birational expression out of it. So hopefully we'll hear more about this general idea later in the day as well. One example that I want to mention that's very related is that in 2013, Einstein and Propp introduced piecewise linear and birational lifts of row motion via the toggles. So I'll get to that in a second. But let me just mention that there's a lot of remarkable facts about these lifts, which is one thing that we notice is that a lot of the theorems that are hold at the combinatorial level actually hold at the higher levels as well. So for example, I mentioned the fact that row motion for this delta n minus 1 poset has order 2n. That persists for piecewise linear and birational row motion of this particular delta n minus 1 poset. It's surprising because for other posets, these lifts don't even have finite order. But for this special poset, they have a very nice order. Okay, so now let me explain how this works in this case. So it's based on this idea of Richard Stanley of associating posets to a polytope. So the order polytope and the chain polytope are two polytopes associated to any poset. The chain polytope is the one I'm going to focus on. Its facet description, so we have coordinates for all of the poset elements x sub p. They all have to be non-negative. And also, if we take the sum along any maximal chain, so a chain is a subset of pairwise comparable elements. If we take any maximal chain and look at the sum of the coordinates there, we have at most 1. And so what Stanley proved was that the vertices of the chain polytope are the indicator functions of the antichains of the poset. So for example, for this 2-element poset, which is a chain, the antichains are 0, 0, 1, 0, and 0, 1. Those are the indicator functions of the antichain. So we get a triangle for our chain poset. For this 3-element poset, the triangle, there's 5 antichains. Those are the Lalanne number many. And those are the vertices of this 3-dimensional chain polytope, which also has 5 facets. Okay, and so in order to do this like piecewise linear toggling, we work at the level of the chain polytope. So here's how we define the piecewise linear toggle. It's an operation on the chain polytope. And it's defined like this. So if we look at the kind of q coordinate, and q is not equal to p, then we do nothing. So we're only affecting the p coordinate. And at the p coordinate, Well, there's this formula, which is a little bit complicated to think about. We get a new coordinate, which is 1 minus the maximum over the sum of every maximal chain of the values in that maximal chain. But let me give you a geometric way of thinking about it. So really what's going on is this tau sub p, the piecewise linear toggle, reflects our point in the chain polytope within the line segment in the direction of this coordinate direction, x sub p. So if I'm at this point pi here, I draw a line in the direction x sub p, and I reflect my point within this polytope. That's what this formula is doing, because this max over all maximal chains of the sum is basically like the maximum, is the first facet that I'm going to encounter in the direction of x sub p, right? So that's what it's doing. It's saying, look for the first point where I'm going to leave the polytope and give me the complementary value there. Okay, and the thing to notice is that when we restrict just to the vertices, which correspond to the antichains, then these piecewise linear toggles actually recover the just ordinary combinatorial toggles of the antichains. So that's why they are a piecewise linear lift of those toggles. So as before, we can combine all the toggles in a given rank, and what we do is we define the piecewise linear LK involution to be, of course, the corresponding composition of rank toggles for the piecewise linear toggles. And now it's acting on the chain polytope of this delta n-1 poset. And what we showed, this is kind of what we're really interested in, is, well, the properties of the LK involution lift to the piecewise linear realm. So first of all, it's an involution, and secondly, the analog of the fact that it exhibits the symmetry of the Narayana numbers is if I take the sum of the coordinates of one point in my chain polytope pi, and I take the sum of the coordinates of its image under this piecewise linear LK involution, then I always equal to n-1. So same symmetry as before. Let me do one quick example. So here's some point in my chain polytope. Here's its image under the LK piecewise linear involution. I'm not going to show you how to compute all of these, but here's one example. So one of the first toggles we would do is at this thing in the bottom rank. And why is this equal to 0.1? Well, I did this. I did 1 minus the maximum of the sum of all chains that contain this thing that's labeled 0 here. And it turns out the maximum there is 0.9. So I do 1 minus 0.9 and I get 0.1. And another thing you can check is that if you take the sum of all of these values on the left and the right, you get 4, n-1. So there's all kinds of fractional values, but they add up to just this constant 4, no matter what point I started with on the left. Okay, sorry, I'm going a little bit cuckoo here, but I want to get to the birational stuff because it's birational combinatorics. Okay, so we know that algebraic geometry studies sort of polynomial expressions that look like this, and they give kind of curvy things. Tropical geometry studies piecewise linear expressions that are like maxes and mins of linear things, and that gives sort of flat polytopal complexes. And there's this idea that we can move between these two worlds of polynomial expressions and piecewise linear expressions via these two processes of tropicalization and detropicalization. So tropicalization takes us from algebraic geometry to tropical geometry by replacing every multiplication n plus with a plus and a max. And detropicalization does the opposite. It takes the plus and max to times and plus. And I'm kind of being a little, I'm treating tropicalization and detropicalization like they're analogous, but they're not analogous. One direction is sort of well-defined and the other one is ambiguous. Detropicalization is not really a well-defined process, but anyways, it's more of an art. And via this kind of art of detropicalization, Einstein and Propp also introduced birational toggles. So the formula for the birational toggles is basically you take the formula for the piecewise linear toggles that I wrote down here as a piecewise linear expression, and you just kind of do this detropicalization, even though it's not quite precisely defined. But what you get is an operation now on kind of labelings of your poset by complex numbers. And again, the formula is exactly the same as long as you interpret everything correctly and kind of convert the plus and the max to times and plus. And there's also this little wrinkle where you have to fix some extra parameter kappa, which is kind of the one in the piecewise linear realm. Okay, but with these definitions, we can kind of, in a straightforward way, define the birational toggles. Note that there's kind of division going on, so they're not really defined everywhere. That's why I'm writing them as like dashed, birational maps. But now we do the thing that you'd expect, which is we define the composition of the right composition of toggles to be the birational LK involution. So exactly the analogous thing. And we show that even this one has the same properties. So it's always an involution. And now the analog of the fact that it sort of exhibits the symmetries is if we take the product of all the coordinates of 1 point pi and multiply that by the product of all the coordinates of its image under LK, then we get this fixed constant kappa to the n-1. So again, kappa is sort of our stand-in for the constant 1. And instead of n-1 times 1, we get sort of 1 raised to the n-1, but actually it can be anything kappa here. Oh, the dashed arrow, that means it's a rational map. So it's not defined everywhere, but on an open dense subset it is defined. Okay, so let me give you just one example. I'm close to wrapping up here. Yeah, so this is what the LK involution is for delta 4, and for the birational version. You can see what we get are, it's kind of easier to write the birational one because now we just get like sort of polynomial or rational expressions in our initial input u, v, w, x, y, z. And there's different things we can check about it. Like the fact that it's actually an involution means that if I take this expression, but I plug in for z, x, y, these 3 things, what I should get back out is x. And that's like a non-trivial computation of, clearing denominators and so on. And also the other thing is the symmetry property says that if I multiply everything together, what I get is kappa cubed. So you can check that if I multiply everything on the left and right together, the only things that don't die are these 3 kappas on the bottom. In fact, we kind of show that there are some more refined symmetries. Let me not get into the details here, but basically we show that you don't have to multiply together all of the left and all of the right. Instead, you can take sort of a subset, this V-shaped subset, multiply everything in there times everything in there, and then you also get a constant, which is just like kappa squared in this case. So we show that there's not just one symmetry of LK like this, there's sort of n-1 symmetries of LK for every poset delta n-1. So there's kind of refined symmetries. Okay, I did want to get to this final section though, which is about the why I care about this, the so what, right? Okay, so I'm going to give you a few reasons that this is interesting. Okay, so the first is actually maybe not such a good answer, but it's the fact that these results are more general. Why do we care about these lifts? Well, all birational identities tropicalize, but the reverse is not true. So proving things at the birational level is strictly stronger. And there's even things above the birational level. So there's this non-commutative stuff that Tom and Dari have been interested in recently. I think we're going to hear a little bit about non-commutative dynamics or algebra later in the day. So that's interesting too. There's even higher realms to aspire to. But maybe that's not so convincing. Well, we can always generalize, but here are some more specific reasons. So even if you just care about combinatorics, the piecewise linear realm is interesting because if I look at the rational points in the chain polytope with denominator dividing m, then there's only finitely many of those, and they actually have a nice combinatorial interpretation. So for example, for this particular poset, they correspond to m tuples of nested Dyck paths. So kind of like if m equals 4, I get 4 Dyck paths, which are stacked inside of one another. And they show that, our operation shows that the corresponding Valley generating function of these tuples is symmetric, and it demonstrates the symmetry combinatorially. Let me skip over this, but this is saying that it's interesting to consider that same composition of toggles, Rowvacuation, for other posets, in particular for other root posets. And we show that for these other root posets, at least for some of them, like the classical types A, B, C, and D, that this involution again demonstrates the symmetry of the corresponding Narayana numbers. So this is like a problem in Coxeter-Catalan combinatorics. And basically by writing our involution as in terms of these toggles, it suggests a new operation to consider for any poset. Okay, let me mention these last two things. So number 4, why might this be interesting? Well, we'll see later on a lot of beautiful algebra like geometric crystal, geometric RSK, and connections to things like cluster algebras that are closely related to these birational toggles and to row motion. Right now, I don't know anything about Rowvacuation or the Lalanne Kreweras involution. I don't know how that connects to any of this, beautiful algebra, but I think there could be something going on there because you see very similar kind of birational expressions. And also in terms of algebraic geometry, I think these birational lifts could be interesting because they give us some interesting birational endomorphisms of affine space. Well, for one thing, they have finite order, which already is kind of interesting for a random, endomorphism of affine space. So for example, it could be worth looking at the variety of fixed points of these operations. And also, I think Mike will mention this in the discussion, but we have some conjectural invariants. So right now I was talking about sort of symmetries, which are like sending one thing to its sort of its inverse. Invariants are kind of the dual of that, where something doesn't change when I apply this operation. But we have some polynomial invariants that we have conjectured, but we don't know how to prove. Okay, so I should stop there. Thank you very much. Yes, they're very pretty.
What is the sound of 4 hands clapping? Thank you very much for a great talk. Really interesting to see all that put together, and it's a great collection of lifts.
Yes, thank you.
Any questions from the audience that hasn't already been asked?
Or answered.
I can ask one if real quick. Can you elaborate more on what fails an exceptional type?
I see. For this result here. Well, what fails is, well, you still get an involution, but it happens that there are a couple of antichains that where if you look at the size of the antichain plus the size of its image, it doesn't quite add up to the right thing that you want the rank. I don't know why that happens. I mean, I guess I don't know why it works in some cases and doesn't in others. It's not exactly motivated from the Coxeter type stuff, but maybe there's a small change that you can make it work. This is actually a problem. So this is something Panyushev highlighted, but to show that the Narayana numbers for any root system are symmetric. But if you use this definition, the number of antichains of given size in the root poset, it's not at all obvious, even less than in type A. And so I think it's still an open problem to really explain why this is true. But one way to do it would be to find a connection from non-nesting and non-crossing worlds, which is still elusive, I guess. But another way would just be to stay within the non-nesting and find an involution like this. We use this work of Armstrong, Stump, and Thomas for this result. So I should have mentioned that, I guess.
I have a question. So how do the Q Narayana numbers fit into this, if they do at all?
Q Narayana numbers. To be honest, I don't even know the definition of those. So I'm not sure is the answer. What is it area of the Dyck path, or what is the statistic for Q Narayana numbers?
As I recall, it doesn't have a simple interpretation in terms of this Catalan model. So
okay, well, yeah, that's a good question. I haven't thought about it all, but yeah, I'd have to look up again what the meaning of it is. Gabe, yeah?
Hi. Yeah. So I'm more familiar with the version of all of these maps for order ideals rather than antichains. And so like at the combinatorial level, it's easy to go between antichains and order ideals. You just kind of down close the antichains. But is there a connection between these two ways of thinking about it at the PL or birational level?
Yeah, that was something I was definitely sweeping under the rug. The fact that there are sort of two coordinate systems here, as Gabe was saying. One of them is like anti-chain that I was working in, but the one that people prefer usually to work in is the order ideal coordinate system. But in fact, there is a straightforward way of translating between them. At the PL level, it's what's called Stanley's transfer map between order and chain polytopes. So in this initial paper where Stanley defined the order and chain polytopes, he defined this thing called the transfer map between them. It's not an integral equivalence, but it's basically some kind of continuous piecewise linear equivalence. And if you use that, that really is just a formal procedure that you can go through to translate from one to the other. And then for the birational, I think this was worked out by Mike and by Tom maybe as well, but you can use actually probably Jim and David knew about it as well, but you can just birationalize the transfer map, and that also, again, it's kind of a formal thing to just convert between the two coordinate systems. So.
Okay, so sort of things that you prove about Rowvacuation in terms of the anti-chain.
There's a commutative diagram, and you can always push it through that. Yeah.
Okay.
I knew that was going to be an annoying technicality, but it's easier to state things for antichains here.
And then it's not. Is it? I guess if you're talking about you were starting with symmetries of Dyck paths, so they're like the antichains. Like the thing that you were counting was the number of points in the antichain. Right.
If you're talking about order ideals, then you can say like the number of maximal elements of the order ideal.
Okay.
Or the number of minimal non-elements, or what? Like there's So it's just a slightly different statistic on order ideals, but it's the same thing. Yeah.
But toggling is complicated between the two pictures. It's not the obvious thing.
To convert toggling from one to the other.
Yeah, this is what Mike worked out.
Right. Yeah, there's this so for the order ideal version of rowmotion, you toggle from top to bottom, and for the antichain, you toggle from bottom to top. So already that's a little bit interesting difference. Yeah. And yeah, Mike worked out most of this.
Yeah.
Okay, I think probably over time.
Make sure Mike has time to talk about things. So, so thanks so much, Sam. That was a great talk, and it's good that there's still questions. There should be time at the break to do more with that. So, Mike Joseph, are you ready to be a discussant? Awesome, thank you.
Mike, is it okay if I keep recording?
Is it okay if we can hear you? Let's see, you're still muted.
Yeah, but I don't think he's forcibly muted.
Uh-oh.
Has to unmute.
Okay. We're good.
Oh, there we go.
Can
we keep recording?
I'd like to thank Tom and Dari for inviting me to speak. So yeah, I've never done a conference in this format before, but we're going to have a little bit of discussion on Sam's talk. So nice talk, Sam. And I wanted to discuss, start there's a lot of avenues that you can take when you're exploring things in the birational realm. And as Sam described, as kind of an art form, how do you detropicalize? How do you define a birational lifting of a combinatorial action? Maybe, not everything can be lifted. So, first of all, it's like how did we discover that the LK involution can be expressed as this composition that's Rowvacuation? And here I'm actually subscripting Rowvacuation and rowmotion with A to indicate that we're doing the antichain version of this. Well, it started with just the question of, is there a way to lift the LK involution to the birational realm? And this was a natural question to ask because, first of all, on this particular poset, rowmotion satisfies nice behavior. The periodicity, a lot of the homomesses at the birational level, or at the combinatorial level, lift to the birational level. And also the LK involution is related to rowmotion via this identity. So this was a natural question to ask, which could that be lifted as well? But, this description we have doesn't lead to a straightforward way to lift it to the birational realm. This is, asking, okay, if something is in the antichain, well, here you don't have an antichain. You have a, even in the PL level, you have a, it's not clear how you would lift this to the PL level either, the piecewise linear level. So, if we were to find a lifting, we wanted it to, hopefully to have, these four main properties generalized. It to be an involution, the second one, so it forms a dihedral action together with row motion. The symmetry of the cardinality, or the number of values is the cardinality of the antichain. There's also another statistic that is exhibits the symmetry, and that's the major index of the Dyck paths. So in fact, Jim asked about the Q-Nariana numbers. I don't know about those, but the Nariana numbers count Dyck paths by cardinality, and the Q-Catalan numbers count Dyck paths by major index. So those are both symmetric. Well, actually, we're looking for a birational map. So we want, instead of plus, we want times, and so on and so forth. We're looking for a birational map that's hopefully satisfies these. If it doesn't satisfy any of these, it's probably an uninteresting map. If it satisfied three of these four, it might probably be interesting, but we actually found one that satisfies all of these key properties from the combinatorial realm lift. And there's a fifth one that's important. In order to actually be a lifting of the LK involution, it needs to give you the LK involution when you detropicalize and restrict to the antichains of the poset. So let's start with how did we find such a map? Well, let's start with a simple example. Yeah, Gabe.
What is the birational version of the major index?
So basically, whatever column you're in, like in the you would raise that to like an exponent. Like it's like a product, but weighted, weighted. So like things in the product of all the labels, but like depending on what column it's in, it would have an exponent on that.
Oh, okay, and the cardinality just lifts to the product of all the elements.
Yeah, so that's a good example. So the cardinality is something that naturally lifts to the birational level, because the cardinality is just this. If you think of the antichain as just zeros and ones, one if the element's in there, zero if it's not. The cardinality is the sum. So when you detropicalize, that becomes the product.
Okay, that makes sense. Thanks.
So, well, first of all, we're going to get some linear algebra. But if I just look at the row motion orbit of this, the birational antichain row motion orbit of this, I get some, we start with labels x and y and z, and we get some x plus y. We get a kappa that, a kappa is just, it replaces one when we detropicalize. Then when you do it 3 times, you actually get a horizontal reflection of the original one. And so, all of these labels we get are, of this form. They have these 5 factors. So maybe, it would be natural to look for the same thing for the birational LK. If we can define the birational LK on this poset, that maybe the labels would also have this form. So this is actually the linearization philosophy that I learned from Jim Propp. So I'm thinking of these exponents as actually coefficients. When we tropicalize and we try to get something that lines up with the LK involution that we know in the combinatorial realm, what would these coefficients have to be? So let's just try to come up with what would this corner label have to be. So so here we have in this left one that gets sent to itself. Well, C1 is always there because that's multiplied by 1, which is and then here Z is 1. So C1 plus C4 equals 0, because when you apply LK to this bottom left corner is not included. Here, C1 plus, so X is 1, Y is 1, so plus C2 plus C3, And then the max of x and y is 1. So plus C5, that also equals 0, because when you apply LK, you want this to be a 0. Here, nothing is included. So with C1 is still, everything else, x, y, z, is 0. So C1 equals 1, because when you go over here, this is included. So C1 equals 1, and you can come up with similar equations for these two over here. And then this is just so we boiled this down to a linear system, and this actually has a unique solution. So this C1 is 1, C2 is -1, C4 is -1, these others are 0. So yeah, so when we, the detropicalized version, that -1 is an exponent on x, that -1 is an exponent on z. This 1 means kappa to the first power. That's also an exponent. So there's actually, do this process for 3 of these labels to figure out what these should be. By symmetry, this one's kappa over xz. By symmetry, this is going to be kappa over yz. And then we're actually going to find this top one. We could do this exactly the same way, but we're actually going to do it a different way, because especially when you move into, this is a simple example, but when you move into higher, when you move into bigger posets, the labels get uglier and uglier. This was a shortcut that was often helpful. So we want the cardinality, the birational cardinality is the product of the labels of this times this to be kappa squared. So what should this label at the top be?
So Mike, unfortunately, we don't have a lot of time. So can you maybe try to make this discussion happen quickly?
Okay. So we want this product to be equal kappa squared. So we it's going to have to just be z. And so, and then you check, does this satisfy this property? Is this an involution? Does it, when you do row motion and then LK, is that the same thing as LK and inverse row motion? Is like, oh, cool. This at least here on this small poset, we found an analog, and then you move higher up, and it gets a little bit more complicated. You have more complicated factors, but we worked out these examples, and like, okay, so what's the pattern? But yeah, I don't know. I mean, am I out of time, or I wasn't sure because we had the question period of the.
We started late, but let's say you have let's say you have 2 more minutes. We have to start at 10 early, at 10 precisely.
Okay. So there's certain posets that, as Derek commented, that there's certain posets where the order of birational row motion is finite, and on these posets, it's natural to ask, okay, what other notions that are defined in the literature, which of those could be lifted to the birational realm? And so Panyushev in the paper where we define this duality map, that's the same as the LK map on antichains of the type A root poset, define this invariant. I don't have time to go into the details of, so invariant actually under row motion and under Rowvacuation, or under row motion and the LK involution. So it's like, was there a way to define this? And it's not obvious, the way it's defined, it's not at all obvious that you even could lift it. So, we went through that same, like, start with small examples and figure out how you could do a lifting, looked at the factors that appear when you do iterations of row motion, birational row motion. And yeah, I mean, I'm not able to write the definition here, but it's in our paper. But we actually don't know how to prove it's invariant under birational row motion or birational LK, but it is easy to see that our equivalent description is actually the same as it's equivalent to the definition given in Panyushev's paper, which it's not hard to show that, but we wouldn't have come up with this equivalent way of describing it had we not been looking at the birational realm. And that's another, I guess that's maybe the last point I want to make, is emphasize that One reason to look at the birational realm is that you often observe new things, even just about the combinatorial maps you're studying, that you wouldn't have discovered otherwise.
Okay, thanks a lot, Mike. I wish we had time for questions. At this point, we probably don't. So let's just
Thank Mike again, yeah.
Okay.
I think we should give people at least like a 3-minute bathroom break and then start then.